Hi, I am Ashim Datta. I'm a professor in the Department of Biological and Environmental Engineering at Cornell University. This short module is in a series intended to help recap the math that might have been done, a year or two earlier, before taking an undergraduate course on heat conduction or mass diffusion. This particular module has to do with one example of a non-homogeneous equation, and we want to do this in cylindrical coordinate, and also we want to use the simplest boundary conditions where the temperature is given. So this equation that we are interested in solving is like this: del del r of r del t del r plus q equal to 0. So in other words, this equation 1 over r del del r of r del t del r is equal to minus q over k. So this part is not 0. That's what makes it non-homogeneous. Now, why do we even bother with this equation? Because it comes up in case of steady state heat conduction or steady state mass diffusion type of physics. Okay, so now let's write the equation and try to solve it. So our equation is k times 1 over r d dr of r dt dr plus q equal to 0. And so again, this q and k are constant, and I've taken the liberty to replace the partial derivatives with d, because the independent variable t is a function of only one variable r. Okay, so let's proceed in solving this so we can uh, rewrite the equation like this, equal to minus q over k times r. So integrating once, I get r dt dr equal to minus q over k r dr plus c1, and so we get dt dr r dt dr equal to minus q over k r square over 2 plus c1. So dt dr is minus q over 2k times r plus c1 over r, and so integrating again, we get t equal to minus q over 2k r square over 2 plus c1 natural log of r. So this 1 over r integrated gives me natural log of r plus c2. So this is my general solution. We still have the c1 and c2 as the unknowns, and again we are going to use the simple boundary condition of t at r equal to r1 equal to t1, and t at r equal to r2 equal to t2. So if this is like a cylinder, then at r equal to r1 the value is T1, and R equal to R2, the value is T2. So substituting the two boundary conditions, we get from BC1 we get T, or the first boundary condition, at T1 is equal to minus Q over 4K times R1 square plus C1 natural log of R1 plus C2. And using the second boundary condition, I can get T2 equal to minus Q over 4K R2 square plus C1 natural log of R2 plus C2. Okay, so now of course we have to evaluate C1 and C2. So for that, we do like we did in other cases, we will subtract the first one from the second one. So we get T2 minus T1 is equal to minus Q over 4K R2 square minus R1 square plus C1 natural log of R2 minus C1 natural log of R1. Okay, so just simplifying further, minus Q over 4K R2 square minus R1 square plus C1 natural log of R2 over R1. Okay, and now we still have to, of course, find C1. So for that, what we do is substitute T1 again from our solution, the general one. So then from that I get again T minus T1 is equal to, so it will be just like this guy, except instead of T2 I'm using this equation. So T minus T1 would be Q over 4K over this R square minus R1 square plus C1 natural log of R over R1. Okay, and so we still have these two equations from which we have to still find C1 yet. So let's do that. So we write T minus T1 is equal to minus Q over 4K R square minus R1 square plus, for C1 I substitute the value from the first one. So from the first one, for T2 minus T1, from there we can write C1 natural log of R2 over R1. Please see previous slide. C1 natural log of R2 over R1 is equal to T2 minus T1 plus Q over 4K R2 square minus R1 square. Okay, and so this means from this equation I can substitute for T1 C1 in here. Okay, so I do that and I get T minus T1 equal to this first term plus T2 minus T1 plus Q over 4K R2 square minus R1 square. Okay, so I'm just substituting from here, divided by natural log of R2 over R1 times the natural log of R over R1. Okay, so this now is my solution. This is my solution, and it's T, the dependent variable, as a function of R, the independent variable. So a few pointers. It is messy, but the one is the process is straightforward. We didn't do anything really special math manipulation. And so the second is, one thing we shouldn't do is do not expand the original equation. What do I mean by that? Remember, the term was K1 over R del R of R del T del R and plus Q equal to 0. Do not expand this, meaning you don't write K times 1 over R del square T del R square plus del T del R. You don't expand it this way. Don't do this. That will just get us into a more difficult situation. And the other thing is, this equation was inhomogeneous, meaning it's not this equal to 0, but this equal to minus Q. So to solve this, then, for non-homogeneous, bring the constants to the right hand side. And finally, for evaluating the constants, we're doing this trick. So we get two things. One, by substituting T2 minus T1 and then T minus T1. We do these two, this one and this one. From that we eliminate a constant. That comes out to be a lot cleaner. Okay, so finally then, to repeat, we have a solution for the non-homogeneous heat conduction equation that in 1D in a cylindrical coordinate. Thank you.